Hello, welcome. So, we are discussing about the flotation. So, we have discussed about the flotation system, that is mainly the flotation has got three main components. One is the chemistry component, that is where we talk about the collectors, frothers, activators, depressions and pH. Then another part is the equipment components, where what type of cell it is, how we will agitate, then what will be the airflow, how many numbers of cells we require, all these things are dealt with this topic, that is called equipment components. And there is another one that is called operation components, that is the feed rate, that is what is that material, at what rate you are feeding, what is the mineralogy, what is the characteristic of that ore, what are the particle size distribution, what is the percentage solids you will be using, what is the effect of temperature. So, normally these three components, that is the chemistry, equipment and operation, they has to be synergized at an optimum level to have my optimum performances of the flotation system. As I told you at the beginning that it is a very vast subject. So, it is impossible to cover the entire topics, that is each component in detail. So, what I will do, I will try to discuss about some of them briefly, which are very important. So, we will start with this, that is the chemistry component, and where basically we call it the chemicals of flotation. Why do we require chemicals? That is the first thing we have to understand. It is basically we said that the separation is made between the two particles depending on their water repellent or water say liking type of your say behavior, we call it hydrophobic and hydrophobicity and hydrophilicity of the particles. But many times we have to have a minimum difference during the in between the degree of hydrophobicity. So, natural occurring minerals may not have that degree of hydrophobicity, or even though they have, the difference may not be that significant. So, we have to control the relative hydrophobicity between the particles, and for that we have to add some chemicals. What chemicals, that we will discuss. And then number 2 is that we said that the bubble has to carry upward the hydrophobic materials, and there has to be a foam formation. But this froth should have certain characteristics, that is after reaching the top of the vessel, if the bubble is burst, then what will happen, again the particle will come back to the cell. So, because you have to collect the froth at a certain rate to take out the materials which are already floated. So, for that the bubble stability is required to some extent. So, for that also we add some chemicals. So, the different types of chemicals involved based on their purpose, that is for what purposes they are used. We normally use the different names for them. First one we call it collector, we will discuss it in detail, what is that collector means. Then the name of the another group of your chemicals what we use, we call them frother. Then there are regulators, the regulators also have got different varieties, like we call them activators, depressions, pH modifiers, like that. So, let us start about the collectors, let us discuss about the collectors, what they are. So, collectors are reagents that are used to selectively adsorb onto the surfaces of particles. That means, it is basically a specific group of chemical which selectively gets adsorbed onto the surfaces of those particles which I want to be floated. It may be your wanted material, it may be your unwanted material. So, when we try to float the wanted material, we have already said we call it direct flotation, and When we try to float only the unwanted material, we call them the indirect flotation or the reverse flotation. Now, they form now why should they be observed onto the surfaces of the particles? What is their role? So, the collectors they form or they should form a monolayer on the particle surface that essentially makes a thin film of nonpolar hydrophobic hydrocarbons. So, that means the this chemical should attack selectively my particles what I want it is to be adsorbed onto the surfaces of those particles, and then once they are adsorbed they should form a monolayer on the particle surfaces in such a manner that a thin film of nonpolar hydrophobic hydrocarbon is formed. That means, I want to increase the degree of hydrophobicity of those particles by this mechanism. Now, how they increase my hydrophobicity? Now, the essential properties or essential purpose of these chemicals should be to increase the contact angle, that is the Young-Dupre equation we have discussed in the last class. So, the collectors they greatly increase the contact angle, so that bubbles will adhere to the surface. That means, the bubbles when the contact angle increases, so the surface becomes more hydrophobic and the bubbles should be adhered to the surfaces of these particles. Now, once the bubble they get adhered to the surfaces of these particles and the bubble for its natural tendency it will try to go up and then it should carry my particle, that is the very purpose of this flotation process. Now, question is what type of collector I will select, how do I know that what chemical I have to use. So, therefore, the selection of the correct collector is critical for an effective separation by froth flotation. Not a single chemical can be used as a collector irrespective of the particle surface properties. So, that is a critical issue, that is for a particular type of mineral or a ore to be floated, what type of chemicals or what type of collector I should use. So, therefore, depending on the mineral surfaces, there are various categories of collectors. So, it can be generally classed depending on their ionic charges, like they can be non-ionic, they can be anionic or they can be cationic. So, there are three broad groups of this, that is it can be non-ionic, it does not have any surface charge, it can be anionic or it can be cationic. Now, in this case the non-ionic collectors are simple hydrocarbon oils, these are basically a simple hydrocarbon oils, while the anionic and cationic collectors consist of a polar part that selectively attaches to the mineral surfaces and a non-polar part that projects out into the solution and makes the surface hydrophobic. That means, what is happening? Now, the non-ionic collectors they are basically a simple hydrocarbon oils, they just sit on the surfaces of the particles and they make the your surface hydrophobic. But the anionic and cationic collectors they have got two parts, that is a polar part and a non-polar part. So, the polar part it should selectively get attached to the mineral surfaces and the projected part of that chemical is the non-polar part, which makes the particle surface hydrophobic. I will show you some examples later on. So, collectors can either chemically bond to the mineral surface. Now, how the chemicals will adhere to the surfaces of my minerals? There can be two broad methods of, or say broad mechanism of absorption. So, one is called chemisorption, or be held by the surface by physical forces, that is, when the collectors can either chemically bond to the mineral surface. When it is chemically bonded, we call it chemisorption, or be held on the surface by physical forces, they will call it physical adsorption. Now, if I group them in the collectors in terms of a flow chart, I can represent the group of broad categories of collectors can be grouped like this. It is, as I said, that it can be non-ionizing, that is your liquid non-polar hydrocarbons, they are insoluble on water like your hydrocarbon oils. Okay. Now, another category is ionizing, that is what we have discussed. These ionizing collectors could be anionic and cationic type. Anionic collectors could be oxyhedral or sulfihedral type. Again, oxyhedrals could be your more applicable or say actually it has got a various say types, like it could be carbonates, it could be sulfates, it could be sulfurates. Similarly, sulfihedral collectors also can be grouped into, that is one is called xanthates, another is called dithiophosphates. Now, as I said that there are two broad mechanisms that how the particles gets adsorbed, that is the collectors, they get adsorbed onto the particle surfaces. One is called chemisorption, that is based on your chemical your mechanism, or another one is by the physical forces. So, in a chemisorption what happens? The ions or molecules from solution, that is the collector has to be dissolved first, and then when it is in solution, it forms irreversible bonds with the surface through chemical reactions, chemical surface reaction. Okay. It is a highly specific process and thus more selective. That means, this process is highly selective because it depends on the whether that targeted material surface likes that chemical or not. It depends on that, and there has to be a surface reaction between these two. Otherwise, this bond will not be stronger and they will not be say getting adsorbed onto the surfaces of those ores or the minerals. In physisorption, ions or molecules from solutions reversibly attached to the surface. So, the first one is the irreversible bond, there is a reversible bond attached to the surface either by electrostatic attraction or van der Waals bonding. That means, you can detach this, you can dislodge this bond by applying some other physical forces, and that is why it is less selective. This is what I was talking about, that is how a collector basically works. So, this part of the chemical, that is the collector. So, that is the polar group. Suppose this is the mineral surface. So, this polar group they get adsorbed onto the surface of these minerals either by the two mechanisms, it could be chemisorption or by physisorption processes, and this part we call it non-polar group, and this gives you the hydrophobicity of that mineral surfaces. So, this is an idealistic view, because what happens now that if the particle surface is not prepared well for this polar group to be attached, or they are not susceptible to this mechanism either by chemisorption processes or by physisorption processes, then these chemicals will not be effective. So, the selection of that collector is very much dependent on what is the surface property of your material. Now, it is also evident from the previous figure that the collectors, it should be optimally added. That means, the doses, how much of that collector, that is, you may have chosen a right kind of your chemical to be used as a collector for a particular ore to make the surfaces hydrophobic. But what will happen? Now, you see that if I am adding, now these surfaces are almost coated with your collector, but if I have excessive of this, so what will happen? They again starts getting your adhered to these say polar and non-polar groups. So, that is why I have written that the collectors should be used in very small concentration, because it adversely affects the recovery of the valuables. Why? Now, because due to the development of multi collector layers on the surface, that is quite evident from the previous picture, that if I have more amount of collector, we will have multi layers of these chemicals onto the surfaces of this material, which is not required, and therefore, it will reduce the proportion of the hydrocarbon part oriented toward the bulk solution, which reduces the hydrophobicity. Because what will happen, say when I am having more of this collector, then this polar and non-polar group will be randomly distributed, which is projected to my fluid phase. So, the selectivity of the mineral surface towards the bubble will be lost, and therefore, the recovery will be lost, and unnecessarily you will be incorporating say cost for excessive chemicals. So, it is not only important that what should be my ideal collector for a particle surfaces to be made hydrophobic selectively. What is equally important also that how much of that collector or that chemical I have to add. So, what is the optimum doses of that collector? And what will happen if I have excessive collector? It tends to it may sit on the surfaces of other minerals which I did not want to float. So, what will happen? So, those mineral surfaces also will be hydrophobic, and they will be also floated along with my wanted minerals which I want, which was supposed to be floated. So, the selectivity will be reduced, as well as my recovery of my valuable minerals, or I would say the material or the minerals which I wanted to float, that will be reduced, and it will add extra cost to the entire process. Additional problems which is not written here, that is this chemicals, excessive amount of chemicals may cause environment related problems, because ultimately that water what is going out of the system, they will be carrying all these unused chemicals, and that may be causing environmental hazards. So, the dosage selection is also very important, and what is the most important thing about the selection of the collectors is that it is not only this, it has to be specific to that mineral surfaces, and then your doses how much I require, and then whether this chemical is easily available, and then can we regenerate these chemicals? These are all the issues related to the collectors in general. Now, let us discuss about the non-ionic and ionic collectors. So, the non-ionic collectors, as I said, that when do I require this? Now, these are required to enhance the hydrophobicities of the partially hydrophobic mineral surfaces. Like take the example of coal. Coal is a naturally hydrophobic mineral. That means, it has got certain degree of hydrophobicity naturally, but many times that much of hydrophobicity is not enough to have an effective separation of the coal and shell particles. So, there many times we use the non-ionic collectors by selectively adsorbing on their surfaces, because they are very low cost materials, they are easily available, and they are many times can be recycled back also. So, that is the fuel and kerosene oil are some of the non-ionic collectors which are used for coal flotation. That means, when we have a naturally hydrophobic mineral, there you may require a little amount of non-ionic collectors, that is something like your mineral oil or the is like your kerosene oil, and then we can use them as non-ionic collectors. But here the selectivity is less. So, except for certain minerals or say like your coal, it is not being used that your it does not have that widespread use. Now, let us talk about ionic collectors, that means, the minerals which are very difficult to float. For that we need some targeted chemicals or targeted collectors. These are complex molecules. So, what are these ionic collectors are? They have complex molecules which are asymmetric in nature and are heteropolar. What does it mean? The molecules have a non-polar hydrocarbon group which is water repellent in nature. So, it should have it must be a heteropolar, that means, or naturally they are heteropolar, and it has got a non-polar and a polar group, and non-polar group is basically water repellent in nature, and the polar group which reacts with water, that means, which likes water or which starts reacting with water. And that is why I said that this polar group should selectively sit on the surfaces of my chemical, and the non-polar part should be projected towards the my fluid, that is the water. So, as because it is water repellent, the non-polar group. So, my particle surface now coated with a thin film of collector will behave like a hydrophobic mineral. Ionic collectors, as I said, that it can be having two types, that is anionic and cationic collectors. If I look at anionic collectors, these collectors possess non-polar and a polar group in the anionic part. That means, in the anionic part it has got a non-polar and a polar group, and the cationic part has no significant role in the reagent surface reaction. That means, the collector has got an anionic part and a cationic part. In this type of your anionic collectors, the non-polar and polar group, that means, basically your anionic part is heteropolar, that it has got a non-polar and a polar group, and that is what we try to use, that property. Examples like carboxylates, it is a oxyhydral your collector. These are also called the fatty acids or soaps, they come into this category. Real example are salts of oleic acid and linoleic acid. Soaps, they have an advantage over other ionic collectors in a way that they have long carbon chains and they are soluble in water. So, what is the issue here? That your collector must be first dissolved into your solution, and then it should have that your cations and anions to be released, and that anionic part in this type of your anionic collectors, it has two polar groups, that is your polar and non-polar part. So, the cationic part does not have a significant role to play, and that polar and non-polar group will try to make my mineral surface, my targeted mineral surface to be hydrophobic. In that context, the soaps has got advantage over other ionic collectors in such a way that although they have got long carbon chains, they are soluble in water. Why I mentioned about long carbon chains, that we will discuss later on. These are basically strong in nature and have low selectivity. This gives you a very stable bonding, but they have got lesser selectivity. Where they are used? So, they are used for flotation of calcium, barium, cerium, magnesium, and your salts of alkali and alkaline earth metals. This is an example of an anionic collector. You see that this is the structure of sodium oleate, very popular collector. You see that it has got a cation part, that is the sodium. Now, within this anionic part, you have got a polar group and you have got a non-polar group here. So, this polar group should get adsorbed onto the surface of my mineral, and this non-polar group should be projected towards my fluid part, so that my entire surface of the mineral becomes hydrophobic. So, if you look at the structure here, it is very fascinating that this is called this is basically a of no use, this cation part, and this is how they are basically oriented towards. So, how big is the chain, how long is the chain, that determines that whether it is a short chain or whether it is a long chain collector. There is another example is sulfonates and sulfates. These are called the oxyhedral. These have lower collecting power and have greater selectivity. That means, it can sit selectively onto your targeted mineral surfaces, but its collecting power is very less, because the bonding may be weak. Bonding between the particle surfaces and this collector may be weak, and that is why its collecting power may be your low, but it will not have friendship, that is in terms of bonding with anyone, that means with any mineral. It will only have friendship or the bonding with a certain class of material or mineral which you have targeted to be floated. So, they are used for flotation of barite, celestite, fluorite, apatite, chromite, cassiterite, mica, kyanite, cellite, etc. Then there are another group of collector, that is called Xanthates. It is also known as sulfihydride group of collectors. So, they are most widely used thiol collectors, also called xanthogenates. They are formed by reacting alkali hydroxides like KOH and carbon disulfide and alcohol. So, how they are made? Now, by reacting with alkali hydroxides, carbon disulfide and alcohol, you can make this type of collectors. They contain normally 1 to 6 carbon atoms. Sodium, the cationic part, and the alkali xanthates decreases in efficacy with age. That means, if it is freshly produced, it will have much more efficiency than if it was produced earlier. This is an example of that, is called sodium ethyl xanthate. See that this is again the cationic part is the sodium. Now, this is the polar part and this is the non-polar part. So, you see that there are structural changes. It has got now 2 carbon atoms and here you have got 2 sulfur atoms. So, this is another group of your collectors. This is also very popular. It is called sodium ethyl xanthate. Now, how does it work? It adsorbs chemically on the sulfide mineral surface and form insoluble metal xanthates. They are used for collection of oxidized ores like malachite, cerussite, anglesite and native minerals like gold and silver, where they found applications. However, whatever the examples I am giving does not mean that all varieties of such ores will have equal responses to these collectors. Why? Now, the mineral surfaces may not be that clean, though the mineral surfaces may be also having some impurities, and there are many other your varieties of parameters could be there. Now, depending on the cleanliness of that material surface, depending on the surface properties of that mineral, the effectiveness of a particular collector will depend. But normally when we start working with that, whether the what type of collector we should start with. So, these are the general guidelines that you can start with this type of collectors based on your mineral. If it does not work, first you have to, before you conclude that whether it works or not, you have to optimize the doses and the other 2 parameters like your machine related issues and your material related parameters. Also you have to optimize and then you can say that whether the collector is appropriate or not. There is another group of collectors that is called dithiophosphates or the sulfihydral collectors. These are basically comparatively weak collectors. It possesses pentavalent phosphorus in the polar group. Also called aerofloat collector, they are effective selective collector for copper sulfide minerals. Now, what it is revealing that for different types of minerals, for different your targets and for different needs, that is how much of that, what is the recovery you want and even the particle sizes and various other factors, they ultimately help you to decide. You have to consider everything before you decide that which chemical as a collector I will be using and how much of that I will be using. We will continue this discussion in the next lecture. Till then, thank you very much.